The problem statement from GATE Physics 2021 reads as follows. The above combination of logic gates represents the operation. We have been given a circuit which is using three logic gates, and we are required to find what does the output represent. The four options are OR gate, AND gate, NAND gate, or NOR gate. This is a multiple choice question with only one correct option, and we need to find the correct option. This is a table depicting the logic gates. So this is the name of the logic gate on your first row, and then we have the algebraic expression. For instance, NOT gate can be represented where the A is the input to the signal, and this bar denotes that this is the expression for the NOT gate. Similarly, AND gate can be as A times B. OR gate is A plus B, and these are the symbols for them. So NOT gate has a right pointing triangle with a circle at the vertex of the triangle. A is input and X is the output. Similarly, AND gate, it's a two input AND gate, so we have A and B are the inputs and X is the output. So for OR gate, A and B are the inputs and again X is the output. And there are other gates that have been demonstrated here. NAND gate is nothing but not AND gate followed by a NOT gate. So the symbol would be this symbol for AND gate followed by the circle at the vertex, which depicts a NOT gate. Similarly for NOR gate, and similarly we have XOR and XNOR. So finally we have the truth tables for them. The truth table, what essentially is this mean? It lists all the possible combinations. So for instance, when there is only one input, it can be either true or false, and then based on these sets of input we try to obtain the outputs. So for instance, in NOT gate, if there are only two possible combinations, that the input is low and the input is high, so we've listed them. Now what a NOT gate does is simply an inverter, so it inverts whatever the input is being provided. So if the input is 0, the output would be 1, and the input is 1, the output would be 0. Similarly, in case of AND gate, what happens? This is a two input AND gate, so we are providing two inputs B and A, and the four possible combinations are both the inputs are 0, only A is 1, B is 0. The third possible combination is B is 1, A is 0, and the fourth possible combination is A is 1 and A is 1 and B is 1. These are the only four combinations possible with a two input NAND gate. So based on these inputs, we try to find the output. Now note that X is A times B, so 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. So this table, which contains all the possible combinations of inputs and corresponding outputs, is known as truth table. And in this specific case, this is a truth table for an AND gate. Similarly, using this algebraic expressions, we can obtain the truth table for all the gates listed here, and for that matter, we can obtain a truth tables for every combination circuit. In our question, we are given this circuit. So let's assume that the inputs are A, the top input is A, the bottom input is B, and let's say that the output we want is Y. So output is Y. Now let's just first look at the top gate, which is depicted in this blue rectangle here. Note that this is a NOT gate, and we know that for NOT gate the output is just the input inverted. So I can write that the value of this node would be nothing but A bar. Why A bar? Because A is the input to this NOT gate, and this NOT gate will simply invert it and be depicted algebraically using the expression A bar. Similarly, if you look at the bottom rectangle in orange here, so the input to this bottom rectangle is B, and this is a NOT gate. So what will be the output of this NOT gate? The output of this NOT gate will simply be B bar, because B is the input to this NOT gate or this inverter. Now let's look at this green rectangle. This green rectangle is nothing but an OR gate. OR gate, and we know that the output of an OR gate, the algebraic expression, if you see from the previous slide, it is just the summation of two inputs. So let's write plus in between. That depicts that this is an OR gate. And on the left side we have the first input. The first input to this OR gate is nothing but A bar. This is the first input to this OR gate. The second input to this OR gate is nothing but B bar. The second input is B bar, right? So what I get, y is equal to a bar plus b bar. Now there's something called a De Morgan's theorem. Or De Morgan's laws, whatever you may prefer. So it says that AB whole bar is equal to a bar plus b bar. There are actually two of them, two laws. Second says that a plus b whole bar equal to a bar times b bar. So we notice that the output here we have obtained is a bar plus b bar, and we know that using this first De Morgan's law, we can write a bar plus b bar as nothing but ab whole bar. Now please note that this is nothing but the algebraic expression for a NAND gate. So note that the expression we came about is AB whole bar, and if you go back to our previous slide here, we know that AB whole bar, so this is A, this is B, this is the output X. So we know that the output X can be written as AB whole bar, and this is the expression for a NAND gate, and we have obtained that AB, the output for this circuit is AB whole bar. Hence we can call this output, this whole circuit can be represented just by a simple NAND gate. Okay, so the answer here would be B, NAND, because we obtained that if the inputs are A and B and the output we obtained was AB whole bar, which is the algebraic expression for a NAND gate. So the correct option here is B. Thank you for listening.